Hello and welcome to What's New in Aerospace. I'm Marty Kelsey and we are coming to you today live from the Moving Beyond Earth Gallery at the National Air and Space Museum in Washington, D.C. Today's show is all about robots. I've got Dr. Aaron Parness from the Jet Propulsion Lab in California, and we've got some friends from the National Zoo, the Smithsonian National Zoo right here in D.C. You might be wondering, how do those things go together? Well, they do, and you're going to find out here in just a few minutes. I want to remind everybody watching online and on NASA TV that you guys can submit questions. Go over to Facebook Live, submit those questions down in the comments section, and we will actually take some of them later on in the show. So let's bring up our friends from the National Zoo. I've got Matt Evans and Matt Neff, and they've got a little friend with them today. So come on over.
Hopefully it's not too loud, we'll see.
All right, tell us what you've got.
So this is a New Caledonian giant gecko from New Caledonia.
Caledonia.
So these guys are one of the largest geckos that can be able to actually climb up walls, which is really neat. And if you guys take a look, they're really good with camouflage as well. So they have this nice tail right here that they can regenerate. So when they're smaller, little babies, obviously they will be food for a lot of other big predators and stuff like that, but at about this size, they're not going to really have many predators at all, but they do rely on camouflage a lot to try and not get eaten. But these guys, not the best pets, they're really quick, and they can bite very hard. So they have big jaws, which they use to get a lot of different invertebrates in the forest, and hopefully not my finger, so we will see. But he'll probably be vocalizing in a little bit. And so they do communicate with one another. He's getting started right now. And so basically it just kind of lets you guys know that either like it'll be scary, so the predator will try and drop the food, or they'll have different vocalizations for territorial disputes or mating and stuff like that. And so keep your ears open and you might hear them.
We've got a couple in the cases back here. They're good climbers.
Very.
They're excellent climbers, which is kind of why we're here today. So if you look at the gecko's feet, you guys will have an opportunity to kind of come up here and look up close. You'll see like little slits that look like files in a file cabinet. But if you actually look closer at about 700 times magnification, you'll see that there are these tube-like structures that are all over those files, those slits. If you magnify that another 30,000 times, you'll actually see that there are little hairs that are coming off those tubes, and they continue to kind of split off. So there's been some publications that have shown that on one gecko toe, there can be at least 2 to 4 billion little hairs that are split off, and it's on 7 different levels, and they're different lengths. All those hairs actually cause an attraction to the surface at a molecular level. So they don't have sticky little toe pads like a frog would that can kind of, a tree frog that can kind of climb and stick. They actually are creating a force that attracts the atoms kind of from all of their little fibers on their toes to the actual molecules on the surface, and causes an attraction, which is called van der Waals force, that causes the attraction. When the geckos actually move forward, it pulls. When they move in the opposite direction, it pulls off. So they kind of can pull themselves forward, and then when they go in the opposite direction, they detach, which just allows them to kind of move as fast and as quick as they can, up to 3 meters per second.
Wow, yeah. That is incredibly cool. Well, thank you guys for bringing the geckos out today. We appreciate it. We're going to let these guys hang around with us a little bit more, and we're going to talk to Aaron about, Aaron, what does this have to do with robots? So thank you guys so much for joining us today.
Yeah, so I work at NASA's Jet Propulsion Laboratory. We've built the robots that are on Mars, the Mars rovers. But in my group, we focus on climbing robots, which is why we're so interested in geckos. As they mentioned, geckos are nature's best climber. And so our question was, is the strategy a gecko uses to climb going to work in space? And I've brought some demos to show some of our robots that use that. So something that you guys may have done at home, you rub a balloon on your head and it'll stick on the wall. Has anybody done that? So what you're doing there is transferring some of the electrons between your hair and the balloon, and you create an electrostatic force. And so the reason the balloon falls off the wall is because that charge bleeds off into the air. I have a demo here where we hook up a little battery, and with a battery you can keep that balloon on the wall forever, well, as long as your battery stays charged. So I'm going to put this one over here on the wall, and you guys yell at me if it falls off the wall, hopefully more than 30 seconds. So in this demo, we're using electrostatics, but van der Waals forces don't exchange any of those electrons. They're just using those temporary forces. And so this is what our Gecko material looks like. This is 1,000 times larger than the Gecko material we have on our pads, and it's about 100,000 times larger than those tiny, tiny hairs on the bottoms of the gecko's foot. And that on-off behavior you get is shown here. If you push in this direction, not a lot of contact, but if I pull in a preferred direction, all of those tips make a good contact with the surface, and it's very sticky. You can see that here. Upwards, not sticky, but if you put your weight on it, like a gecko does when it's climbing, it's sticky. And I think we've got a video of our first gecko-like robot.
Cool, and so when a gecko lets go basically and pulls up, you lose that attraction, and then when it's pulling down, it sticks.
That's right, that's right. So every time the animal's weight or the robot's weight is on the foot, it's sticky. But when you want to take another step, if you're climbing 3 meters per second, geckos are taking 10 steps per second, you have to be able to come unstuck. That's just as important as being sticky.
This is so cool.
Yeah, so this is StickyBot. It climbs smooth surfaces. So it's not quite as complex as the real geckos. These guys can climb way faster and they climb way more surfaces. But that was our first attempt. That video is about 7 or 8 years old at this point. So one of the questions we asked at NASA is, will this work in space? We're using gravity in the robot, and the geckos are using gravity to turn their stickiness on. And so we do a trick that geckos do on the ceiling. You put 2 pads or 2 feet in opposition, and you squeeze them together. So you can imagine that like this. Squeeze together, you're sticky. Pull apart, you're not sticky. And do we have someone that's going to
Yeah, do we have somebody that wants to help us try this out? Come on up.
All right. And what's your name?
Kale.
Come over here, Kale.
You can come all the way over
Right
to the
over
middle here. So this is our robot gecko material. I want you to feel that and tell people what it feels like. Is it sticky like a piece of glue or a tape?
Feels like clay that's halfway through.
Kind of like
Feels
clay,
like clay?
maybe like rubber. Is it kind of like a rubber band maybe?
Kind of.
Kind of. It doesn't feel sticky though, right? Can you feel any of the hairs that are on there?
No.
No, you can't. They're too small to feel, but they're there. So all right, here's a demo. If we pull on this orange tab, not sticky. If we pull on the yellow tab, sticky. You want to try that one out?
Sure.
So Aaron, when he pulls on the orange, tell us what's happening with this.
So when he pulls on the orange, it's in that unpreferred direction. It's pulling those pads away from each other. When he pulls on the yellow, it's pulling them in their preferred direction. You're turning the stickiness on.
What?
Yeah.
I know, it's kind of mind-blowing, isn't it?
And unlike a Post-it note or a piece of duct tape, you can use it over and over and over and over again. You can imagine if a gecko's foot wore out after 10 tries, it would be eaten pretty quickly. So the same with this. We actually tested them to 30,000 cycles. Wow. So thanks very much.
Nice job. Nice job. Let's give him a round of applause.
So we did a version of this up in space. We're interested in using these in space to grapple satellites or to have robots climb around on the outside of the space station, doing inspections, doing repairs. This is one of the grippers that we actually sent up to the space station. So you can see in the video, Jeff Williams, an astronaut, was testing these guys. It works a little differently. It has springs. So you put the springs together. That's what turns the stickiness on. And when you want to take it off, you pull the springs apart and it comes off. So they left this in place in the space station. The other nice thing is it doesn't require any power. So that guy's still hanging on over there, but the battery is slowly draining. Whereas at this one, we left it in place for over a year in our lab and it didn't fall off.
So what would the uses for this be?
Yeah, so we're interested in grappling satellites, or there's actually a lot of garbage in space. You might not realize, but all those rocket bodies that are up there, they just kind of keep floating around. And some of them are dangerous. So actually in 2009, an old Russian Soviet actually satellite crashed into a iridium satellite, and it blew up into a bunch of smaller pieces of space garbage. So you could use a Gecko gripper to go grab onto that space garbage and get it out of the way.
Who would have thought that from this would come that?
That's right. So we do a lot of different climbing technologies. I'm going to show you another system here. We'll turn it on. This one is inspired by biology as well, but not by geckos. It uses claws. So these are sharp hooks that are on the wheels, and they opportunistically find the rough spots on a rocky surface like this. So we'll see if it's connected. And so bears, squirrels, there's a lot of animals that climb with claws, right? But they have a lot of muscles and a lot of sensors in their hands. We were inspired by this robot by a very simple animal, the cockroach. Cockroaches can climb really well, but they have tiny brains. And they don't have any of those muscles in their feet to try and control their claws. And so that's good because our robots don't have that many motors and they don't have that many sensors. So they need to work on their own.
That is so cool.
Yeah, so you guys want to see it again?
I do. So where might we use a robot like this?
So this is a robot that could climb cliff faces on Mars or crawl across the surface of an asteroid. Asteroids are actually climbing problems because there's no gravity. So if you don't grab on, you're going to lose your grip. We have also tested these on a very special aircraft where you can simulate having no gravity. That's something that's really challenging to simulate here on Earth. And so we go into an airplane to test. Do you know what I'm...
Yeah, so a microgravity flight, they fly in a parabola, and that basically means just a giant arch like the St. Louis Arch, and at the top of that, you end up falling at the same rate as everything around you, and you get about 30 seconds of weightlessness or microgravity, and that's where you guys got to test. That's incredibly cool.
Yeah, you're seeing some videos from our testing with this robot, but with its Gecko wheels on it, and it's climbing across different kinds of spacecraft surfaces. Solar panels, thermal blankets, composite materials, things that we construct our satellites out of. You'll also see larger versions of these grippers that are meant for grappling. So this is a big gripper that we worked on with Stanford as well that's grappling a 1 meter diameter cylinder, so almost the size of a rocket body that might be floating around up there. There's over 10,000 pieces of space garbage up there that are bigger than the size of your fist. And those could cause some serious damage if they hit one of our satellites, one of our telescopes, or heaven forbid, the International Space Station.
Well, and what was interesting about that video is, in that microgravity environment, you don't have weight, but you still have the mass. And you could see that big cylinder was turning her around as she was trying to grip it.
That's right. That's why we use the term inertia, which is the momentum, the mass aspect, but irregardless of gravity.
Outstanding.
So we've built some larger versions of these robots that also use claws, and we've got some videos of those. We've taken those to extreme environments on Earth to test them. So places like caves and lava tubes, as well as Hawaii. We went to the volcanoes and tested on the volcanoes. We're basically looking for places that would be similar to the places we find in the solar system. So in the video you see here, you're seeing the claw, but in a linear version, in a gripper that's going to use 24 fingers, each of those fingers with 24 of these sharp claws on it to grab onto a boulder. And this is for a mission to go to an asteroid called the Asteroid Redirect Mission. And the idea was that you could move that asteroid out of the way if it was coming to hit the Earth. So by grabbing onto the boulder, you're able to change the mass of that asteroid, and it would be a near miss instead of a direct hit. So if you've ever seen the movies, I was going to play Bruce Willis in this version. We've also got a climbing robot that uses limbs, a four-legged robot that uses those same grippers to crawl around on different cliff faces and caves on Earth.
That is incredibly cool. Well, I want to remind everybody here in the gallery, if you guys have a question, you can head over to the microphone and be ready to ask those. Also, if you're watching online, you can submit those questions on Facebook Live and we will answer them here. Now, Aaron, I've got a question about what we just saw. Those looked an awful lot like fish hooks.
Yeah. That's right. In fact, they are fish hooks. In our lab, we're trying to use rapid prototyping and use cheap materials, things that we can buy. It turns out a fish hook in that industry has been really good at making things sharp and strong, right? And so why reinvent the fish hook when you can just go to the store and buy them?
And are those like NASA engineered super awesome fish hooks, or are those?
Yeah, no, those are Tiemco TMC size 900 BL fish hooks. And a funny story is we created a worldwide shortage of that particular model. When we were going through a lot of prototyping, we purchased 10,000 of those fish hooks, and we needed a few more. 10,000 wasn't enough, and I kept calling up the fishing stores, and I said, hey, do you have any of this size? And they said, oh, yeah, and they would get back to, oh, no, we looked. It's really strange that they're all out. That never happens. Okay.
And the fish thank you for that.
That's right.
I thought that was incredibly cool the first time I heard that it was actual fish hooks that you guys were using. And I think it's really interesting how you guys are looking at nature and looking at the world around you in order to create these robots and to create all of these different things.
Yeah, so we call it biomimetics or BioInspired Design. And there's so many examples out there in the world that have a lot to teach us. And while the geckos are pretty amazing, you'll notice some of these geckos also have claws. So there's really no one way to stick to everything. You kind of have to match your gripper to the right kind of surface.
Now, you also had a larger version of this that climbed a little bit higher, right?
Yeah, so we have a version of this robot, and we were testing it at the lab. We found the tallest brick building we could. We went up about 6 stories, and it was at that point we realized we couldn't get onto the roof. And so the robot was stuck up there, about 60, 70 feet off the ground. It was starting to get dark. So what do we do? What do we do? And so we decided we would try and catch it. It's not so heavy, and so we got a big net, and we caused it to drive backwards, and ran around underneath it trying to catch it, and we missed. Yeah, but it's a good news is because these robots, a lot of it is 3D printed and made out of reusable components, and so we had a new robot built in about a week.
Now, even though you failed that day on catching the robot, is failure a piece of this process?
Yeah, failure is really critical to actually improving your design. So we practice something called iterative design, where we build it, test it, break it, build it again. So this robot you see here is probably version 8. And so you don't want to get discouraged if version 1 doesn't work. We expect it not to work. And you don't know everything about it until it stopped working. You don't know all the lessons it has to teach you until you've broken it, reassembled it, broken it again. And so this is really how we get our best designs. It's by iterating through.
So that failure is something that you just build on.
That's right. It's
Awesome.
critical for us.
Now, do you guys do a lot of things in teams? I hear you talking about the people that you work with and everything. How important is that team aspect of building a robot that'll climb a wall?
Yeah, so in robotics, it's great because you need a lot of different kinds of people. So we work with mechanical engineers, electrical engineers, software engineers that are writing the computer code, and we also work with the scientists. And I really like being on those kinds of teams where you're interacting with lots of different people. When we were out in Hawaii at the Volcanoes National Park, we were there with the world experts on volcanoes, telling us all about how the eruptions happened, and we were sending robots down into the conduits to try and map those fissures that had erupted about 30 years ago.
Wow, that is really, really cool. So you're actually taking these out into the real world and not just testing them in a lab somewhere, but really trying them out.
That's right. Our group is called the Extreme Environment Robots Group. And so we get to go to all the different extreme environments. We have a new project. Maybe we'll come back and share it with you in a year or two. That's climbing icy surfaces. So we went to the top of Mount Rainier where they have caves that are all made out of ice.
Wow. Any hints on how that works?
Yeah, so it's kind of a screw and a heater that go together. And the reason we're interested in ice is because there's 2 really interesting moons out in the outer solar system. One is called Europa, and one is called Enceladus. Their surfaces are covered with ice, but underneath that ice, there's liquid water. More water on those moons than we have on Earth. And where there's liquid water on Earth, you find life. And so we want to go explore those oceans, those alien oceans, to see if there's something there.
Nice. All right, we've got a question from Facebook. Can the friction from gripping be converted into energy to be stored for use?
Yeah, that's a good question. So the answer is sort of yes, but not a lot of energy. So it wouldn't make for a good battery or something like that. But this has those springs inside of it, and so you can use the grippers to store the energy in those springs. So physically, yes, but you'd be better off with a battery if you're trying to collect a lot of energy.
All right, we've got an audience question.
Yeah, what could you do on Earth with these robots? I know you're thinking about space, but what sort of terrestrial things can...
Are there any Earth applications?
Yeah, it's a great question, and we get it a lot. There's actually a company that's using the patents that we created on the Gecko adhesive to try and make Gecko grippers for the factory floor. So pick-and-place operations, might be assembling your TV screen or some other fragile piece of glass. So right now they do a lot of that with suction cup grippers, which work great on Earth, don't work at all in space. But the Geckos have a couple of advantages.
I'd never thought about suction cups not working in space, but you need an atmosphere.
That's right.
Wow.
Yeah, some people want to make window washing robots out of the Gecko material. It's just a really expensive way to clean your window.
All right, we've got another audience question.
Yeah, this is really, really cool. So I guess my question is about what's your backup if it fails? Like you place the little climbing robot and it goes, but or you pull the tab to make it grip. But if you're going to capture a satellite with this thing and if it doesn't stick correctly the first time, like in your process now, in that iterative design, do you engineer some sort of backup for if it fails, or do you keep engineering it until it's so reliable you don't think you'll need the backup?
Yeah, so the answer is kind of both. So we do a lot of testing on Earth as well as in those zero gravity airplanes, and we have a facility that's like a giant air hockey table where things are moving around and floating on that air hockey table, so we can test. And the failures, we hope that they happen on Earth. So we can perfect the capture strategy before we actually send it to space. But we also have a backup plan. So if you miss, unlike a piece of tape that's going to wear out or super glue that once it's solidified it doesn't work again, the Gecko doesn't wear out. And so we can try again as long as you haven't pushed the satellite into some kind of crazy tumbling orbit. And so that's another place where we get to work in a team. We have to work with the engineers that control the thrusters and the engineers that work on the robotic arms to make sure our strategy is robust in case we do miss. Yeah.
All right, we've got another Facebook question. Are any of them solar powered, and how do they work without direct sunlight?
Yeah, good question. So some of our Mars rovers are solar powered, but Mars is farther away from us from the sun than Earth. So the solar energy isn't as powerful there. And so we also have a strategy that uses nuclear power. So the Curiosity rover has a nuclear power source. It uses the heat generated by radioactive decay to create its energy. So with the Gecko grippers, we don't really care where the energy comes from. We just need a little bit of it to do that squeeze and unsqueeze.
And we see that our I've forgotten what you call it, the robot over here on the wall is still there. How long can it stay?
Yeah, so it was a little bit of a trick question. That would stay up for about a week before the battery runs out. And it's about a third the size of a AAA battery, so it doesn't consume a lot of power. You're just replacing the charge that bleeds off, sort of like rubbing the balloon on your head every 20 seconds or so. That's what's going on.
Nice. How did you get into robots? I mean, did one day you wake up and think, I want a robot that'll climb that wall?
Yeah, well, robots are awesome first, so everybody should be into robots. But I was always into building things, and when I got to college, I realized that engineers, that's what you called people that built robots, and so I studied engineering, and it's been having fun ever since.
Now, you took a class on robotics that was pretty inspirational for you, right?
Yeah, so I took a class at MIT. They have a competition where everyone in the class builds their own robots and they compete in some kind of game. They have it in high school now. It's called First Robotics. The professor that taught that class is one of the guys that helped found First Robotics. That was what sort of set the hook, no pun intended, for me to get into robots. I got into climbing robots when I started learning about the geckos, and we worked with some biologists at Berkeley, at University of California, Berkeley, that were studying geckos and helped explain to us how the geckos stick and how they have their amazing climbing abilities.
Nice. We've got a bunch of kids out here in the audience. What would you tell them if they wanted to come work for you?
Yeah, well, first of all, working at NASA is great. You should definitely come and explore more careers that you might get into in space. But the second thing is to get involved in projects, right? So you have your coursework and your schoolwork, but there's clubs and projects after school, and that's some of the places I learned the things that have been most valuable to me, where you actually get to build and try things out, and where you get to fail and realize that you learn from those failures. So whether that's Odyssey of the Mind or Vex Robotics or First Robotics or any of the other clubs that are out there, do as much of that as you can. Boy Scouts, Girl Scouts, that kind of stuff.
Get involved. All right, I'm going to bring up Matt and Matt, the Gecko guys. If they'll come back up on stage. We've got just a minute or so, and I want to ask them, how did you guys start working with geckos?
That's a good question. So I've always been into being outdoors ever since I was a kid. So I used to be down at the local stream, grabbing stuff, bringing stuff home, freaking my mom out all the time. So I've always just been into kind of the outdoors, animals, how they work, how they interact with their environment, all that kind of stuff. So when you learn about geckos and actually learn the kind of how they're moving and the physics behind it, it's really interesting to learn about. So there's always something to learn.
How about you?
Yeah, I think it's the same story for anyone that really works with reptiles in a zoo. You always get started when you were like 5 years old, going out hiking with your mom or your dad, and so yeah, something kind of struck me. It was actually frogs calling, which they're starting to do right now this time of year outside. And ever since then, I thought it was just the coolest thing. And so yeah, now I'm working with native species, but also Komodo dragons and really cool geckos from the other side of the world, which is pretty awesome.
And somebody can go over to the Smithsonian National Zoo and see these guys on display?
Yep,
Yes.
we have both species on exhibit.
Outstanding. So make sure you head over to the Smithsonian National Zoo and check that out. I want to thank Aaron for coming in today and both Matts for joining us and bringing the geckos. These guys are incredible. If you guys in the gallery have any additional questions that you'd like to ask, we're going to stick around for a few minutes afterward and answer those questions. You can also, you'll be able to get a little bit of a closer look at the geckos here. We'd like to thank Boeing for sponsoring today. And like Aaron said, make sure that you go out, join those clubs, get involved, go out to your stream and see what's around in the natural world. I think that's been one of my big takeaways today is look around you, and that it's kind of interesting seeing people from the National Zoo and the Jet Propulsion Lab kind of have that same background of looking around in their natural world and seeing what's around. So thanks for watching.
Thanks, guys.